Video. Okay, we're gonna just what? What is that doing there? You got what? How many tests in physics? Uh-huh. Ah, okay. Well, the quiz helps you on the test, right? No partial credit. That's tough. No, we just have one more test, and that's the last week of class. We have quizzes coming up. I don't know if there's one this week or not. So there's one last handout on friction. I'm adding a couple things. So we kind of did this thing on wedges on yesterday, and that's we're getting into more complicated systems where you have multiple parts, and you got to kind of explore the friction contribution of all those parts. A couple of the interesting things that we do with friction is you can look at belt friction. So this is where you just have like a belt or a rope over a drum. It's also called drum friction. And I took this. I'm just giving you this on the handout, so we don't have to write it because it's kind of tedious. And the derivation and everything, but you can kind of get the concept of what's going on. When you wrap a belt around a drum, you have a normal force pushing it out all the way around that drum, and you can kind of guess that everywhere that normal force is, there's going to be a bit of a friction going on because again, the boundary surface is kind of contacting all those different points. And this makes a arc. So if the angle that the belt is in contact with the drum is called beta, you can do this derivation, and I don't know. I don't think it's terribly useful to be able to follow it, but if you're curious, I could kind of step you through it. Anybody care? Jose, are you nodding, or is that you don't care? Do you want to go through this, why this is the way it is, or do you want the final formula? Basically is this, and what that means is when you're tugging, the thing that you have to keep a track of is which way is the impending motion again of that belt, right? Because friction is going to go in the opposite direction, and that will tell you which force is going to be larger or smaller. So for instance, this person at T2, there's a hand there, right, pulling on the belt, and the obvious, I mean, the impression is that impending motion is the belt is about to slip this way, right? That means friction is going in the opposite direction to oppose that, right? So if we want the belt to slide to the left, you can kind of agree that that friction force is going to counteract some of that. That means the T2 has to overcome the friction force as well as whatever T1 is providing, right? So T2 in this case is going to be bigger than T1. It's different than, with pulleys, you just assume that it's the same because they're frictionless pulleys and they're ideal, and it's the same tension on either side. with a belt, one side's going to have a larger force than the other. Isaac? Well, just imagine there's like a big weight at T1, and there's a force there of gravity. So T1 might just be the W of the weight. And so if you're trying to pull a weight up and you've wrapped a belt around a drum or a rope around a drum, and you're trying to pull it, you know, you're going to have to pull a harder force than W to get over all the friction that the drum is providing. So T2 is going to have to be larger than the weight that you're trying to pull. That's the point, yeah. And how much larger depends on how much of the angle of that drum is being contacted by the belt. And the formula is T2 equals T1. So if the load was W, right, T1 would be W. And E to the mu B, where mu is the static friction constant coefficient, and beta is the angle in radians of that arc that you're in contact with the drum. So in this case, it looks sort of like pi over 3, about 120 degrees right now, beta is, right? So that would be pi over 3 for that particular problem. If that's, well, the arc is drawn for you, and you can kind of guess based on how much it's in contact, right? If it's like a 90-degree angle here, right, then the arc is 90 degrees. Right? If it's like this, where the two sides of the belt make 90-degree angles, then that arc of contact with the circle is an angle of pi over 2. It's wherever the belt is in contact, yeah. If you go all the way around and make a 180-degree turn, what would beta be? 180 minus? What would beta be if you're going a 180-degree turn? Pi. Because it's in contact for this half of the arc, this half of the drum. Right? What if you do a loop-to-loop and you go, that could be really hard, right? Beta gets really big when you start doing that. What is it? Well, it's more than, you know, you're going 1 full cycle plus an extra pi over 2. So that's like 5 pi over 4, or 3 pi over 2, right? So it's 2 pi plus an extra pi over 2, right? What is that? 5 pi over 2? 5 pi over 2. Right? Yeah. And, you know, the force can get really enormous if you start having that much wrapping around. So, you know, you can use that the other way to kind of hold something, you know, by wrapping it around, then you only have to apply a little force there to keep it up. So that's the other thing. So, so that's belt friction. We're going to have some problems with that. We're not really going to have any bearing problems, but they're interesting, and you can kind of see the idea of how these things actually work. Again, this is on the handout. Is there an extra handout for Alan? And again, this is for like mechanical engineers, but you know, who knows? You know, maybe civil engineers might design structures with, you know, actually, you know, Matthew does a lot of work looking at structural analysis of like these tent structures at the Concours d'Elegance, those the car shows. They put all these tents in it. They all have to be certified by a structural engineer, and those tents have a lot of ropes and everything. Jeez, $300,000 for 10 days for a tent. $300,000? Are you insane? It was a big tent, though, right? Like a city block or something. It's really big. A lot of cars under the tent. Doesn't seem worth it. Yeah, so anyway, that's belt friction. So pulleys are also kind of interesting. With pulleys, there's kind of a similar thing where the pulley might be sitting on a shaft, and you know the opening of this pulley is bigger than the shaft diameter, so the contact is a little bit, it's interesting. As the thing is rotating, the contact point kind of shifts to P2, but there's this area here. It's a little complicated. I can't really explain it. I just sort of read about it the other day. But you end up getting like an effective radius called RF, called the friction, radius of friction. And these have to be given to you in the problem statement. Radius of friction is the radius at which, if you sort of blow this thing up, this circle inside a circle, oh, there's another drawing right here. Erase that. It's like you can see the tangent point it starts to shift because, you know, when you rotate it, it kind of climbs the other, it kind of shifts to one side, and then the degree of that, or the size of that distance RF, you can imagine that there's sort of a circle like that, and the resultant of the normal and the friction force kind of forms an upward force here that's actually combating the downward forces of tension. And it's offset by this RF, which gives you a moment. And RP is the radius of the pulley. So RP would be, RP in this case would be, it's not drawn here, RP would be the distance from here to here, right? This is RP. And then, so that kind of gives you these moment arms, right? So the sum of the moment about P2, this point here where you're shifting your resultant, is going to be like 981 newtons times, you know, RP, radius of the pulley, plus this little bit of RF, right? That's giving a moment that's going in the plus, it's going in counterclockwise direction, you know, and then this T here is giving a moment going in the clockwise, so it's minus T, and the radius is RP minus RF. That's the 52 is this guy, the 48 is this guy, and so the tension T on the other end of this thing, where you got a 981 Newton load, you got 100 kilograms there, you're trying to pull it or maintain equilibrium. The T is 981 RP plus RF over RP minus RF. That's, I guess, if you're trying to make it move, actually you're not just holding, you're trying to make it move, you're trying to pull it up. So with impending motion going in this direction, you're getting a little bit of friction, right? Whatever RP plus RF over RP minus RF is, this will be a number that's going to be greater than 1, right? So in other words, T is going to be larger than your load of 100 kilograms if you want to hoist it up with a real pulley that has a little bit of friction. So it's not a huge amount. Yeah. Pardon me? Yes. 48 millimeters. Yeah, because RF, is it given to us here? RF is, it's not written, it's actually R sine of phi. Oh, and you can actually find RF knowing what the coefficient of friction is. That gives you F over N, which is the tangent of phi. And knowing what phi is, you can take R, which is the R of the shaft, which is 5 millimeters, times the sine of phi, and that will give you RF. Wow, yeah, I haven't done this before, and we're not going to do any problems with this, but it's just sort of interesting. But we are going to do problems where you're going to have these sort of systems. Usually it's just like a block and a peg, but here's a system with a pulley in it, and you can kind of get a sense of just the big picture. I think it's useful to kind of just see how this all sort of shakes out. It's kind of interesting when you have a complicated problem like this. So we have to determine the minimum force needed to move block A, and whether block B is going to slip or tip at the same time. So once again, you know, it's a complicated system, and we have to be able to break it down into pieces and analyze it, you know, piece by piece, and put it all together and kind of come up with an assessment of what's going to actually happen, right? So you have to actually assume certain things, and typically, basically, you kind of start here with the boxes, and then once you find out what the force is to get something to move, you just sort of propagate that force, because this is going to be just a, you know, you're going to have to pull harder to get around this peg here, which is basically belt friction. And you're going to also have to pull harder to get around this pulley here, which is pulley friction, right? Just applying those formulas, you're going to increase the force after you cross each one of these components. But the basic question is, you know, how much P are you going to need to apply to get that box to move, right? So you start there, and then once you get that answer, you kind of pull it and apply it to other points. So it's the typical analysis with blocks, is that we start with the assumption, we make an assumption, and here we'll make the assumption that it's going to slip between A and B, not tip. And if it's going to slip, that means we got to the maximum friction force. So that the friction force, we should actually do the free body diagram. And again, I want you to remember when we're doing these free body diagrams, the bodies are separate. There's nothing touching the bodies. There's no ropes. There's nothing on them. There's just forces applied to the body. That's really important. It was missing on a lot of your guys' free body diagrams. So there's a weight on the top box. It's given as 40 newtons. Okay, there's a normal force at B. You can imagine it's going to be sliding. Well, one way, it looks like it's going to be sliding to the left because friction force is pulling away. It's like if we start tugging at this box A, it's going to be pulling B to the right, right? The friction force is going to be responsible for pulling that thing to the right. This is box B. And there's a tension at B going on here as well, right? So there's a counterclockwise moment from the friction force balanced by a clockwise moment from the normal force shifting to the left, right, to maintain equilibrium. Okay, box A has a tension here. We'll just call that TAC. Okay, and we're going to have the weight of the box itself applying sort of in the middle there. We're going to have this normal force NB applying somewhere over here. And we're going to have a normal force at A pushing up the crate or the box. And which way is friction going to be acting on A? At the bottom. Yeah, friction's going to be going to the left. And what about on the top surface here between these two boxes? Which way is friction going on box A? To the left, right? Equal and opposite of FB on box B, right? Those act like internal forces to the whole system, but when you break them apart, you can expose them. That's the kind of what we learned in chapter 7. Okay, so the fact that we're slipping between A and B means that FB has reached its maximum. And then the other assumption we'll make is that maybe B is tipping, and that we'll see what that does for everything, right? So for box B, we do the sum of the FYs, and that's going to give us basically, obviously, NB is basically just WB, which is 40 newtons. And we know that, therefore, FB, which is going to be mu sub B times NB, that's going to equal mu b is given as 0.4 up here, so that's 0.4 times 40, so that's going to equal 16 newtons. So then we can turn to box A and do the sum of the Fy's equals 0, and that tells us that NA equals, again, NA going up has to equal NB plus WA. These are easy problems because everything is vertically aligned. And since WA is 100 and NB is 140, that means NA is 140 newtons, pushing up those two boxes. And of course, if there's a slipping, oops, there's only one P in slips. Or basically A slips, then Fa equals mu A NA, which is 0.3 times 140, which is going to equal 42. What? 0.3 times 140. Yep, 14 times 3 divided by 10. Yep, 42 newtons. And the sum of the Fx's is going to be TAC, means TAC in the positive direction is going to equal the other forces going to the left, which is Fa plus Fb. So therefore, the tension at AC is going to have to be 58 newtons to get that thing to move, to overcome those two friction forces acting on the box. So that's the condition where box B is slipping on A, and it's, that's the force we're going to need on A to get it to move. So we then continue, just to kind of take this all the way through, even though we're going to have to examine the other case as well. We're going to take this through and look at what's going on at C now, to kind of show you how you deal with the belt friction, right? So you've got, at C, you've got a peg on which you're going to have a tension TCD and your tension TAC that you already found, and an RC given to us. Actually, sorry, it's a mu C, an RC and a mu C for that surface. The RC doesn't really matter, it's just the coefficient friction, and mu C equals 0.4. And if we look at TCD and TAC, which one do you think is going to be bigger? Sorry? TCD, what? Mm-hmm. Yeah, right. You've got to apply 58 newtons to get the box to move, but wrapping it around the peg means you're going to have to pull even harder to overcome the friction that's going to try to resist that motion of the belt of the rope around that peg, right? Does that make sense? So TCD is greater than TAC, and that's the trick to understand where the larger force is, because sometimes it's different. Like, there's a problem I think we're going to look at with a like a boy hanging on a rope over a cliff, and can the can the woman hold him up, keep him from falling? That's different. Figure out where now in some circumstances the friction will help you. In this case, the friction is requiring more work. And so we set it up using that formula on our sheet, which is once you figure out which force is bigger, T2 is the larger one, then you can use this formula. If it turned out that T1 was the larger one, you have to invert the formula. So then it becomes e to the minus mu b or whatever, right? So T2 is bigger, so therefore T2 equals T1 e to the mu b beta. Yeah, like if you knew what TCD was and you're trying to figure out what TAC is, TAC is going to be smaller. Let's just write this formula up. So TCD is a bigger one, so TCD equals TAC e to the mu beta, right? Because that's going to give you TCD larger than TAC, right? But suppose you knew what TAC was and you want to figure out what's TCD going to be on the other end of that thing. Suppose you're pulling at this thing with 100 newtons. What's the force going to be transmitted to the box, right? You might want to find that out. And it's going to be smaller because you're going to be having to, overcome friction. Friction's going to suck up some of that force you're applying. So the reciprocal of that formula, solving for TAC, is you divide both sides by e to the mu beta, right? So TAC, and you could write this if you want, but it doesn't really matter. TAC equals TCD e to the minus mu beta, right? In that case, you're going to have the smaller one, right? But that's sort of immaterial. Sticking with the original formula, we're trying to find TCD. So TCD is going to equal TAC, which is 58 newtons. What's mu? 0.4. And what's beta? Pi over 2, 90 degrees. So therefore, TCD equals 108 newtons. So it's almost double the amount of force you need because of that peg. Question, Isaac? It's pi over 2 because that's how much of an arc is being covered by the belt. That peg, if you blow it up, right, and it's sort of where the tangent starts and where the tangent ends is 90 degrees. So the belt is in contact over a 90-degree arc. It's the angle of the arc of contact, right? So an arc like that is a 90-degree arc. An arc like this, maybe 45 degrees, pi over 4. Is it the unit circle stuff? I mean, there may be some unit circle stuff on that. I'm not sure. The size of the peg doesn't even really matter. It's just the arc that you're covering it. So then we got to figure out what's the pulley going to do to it. Well, the pulley has some friction, and they told us the radius of friction is 2 millimeters of that to make it a little bit simple. And the pulley itself has a radius of 25 millimeters. So this is RP, and that's RF. Bless you. And we've got a thing here where we're going to have TCD on this end and P on that, and this R is the resultant of the normal force. And so basically this is the opposing friction and support from the pulley. And it is off the center of that pulley by exactly R sub F. And this is our R force. We don't really care what the R force is, we just want to know what P is. So we can do the sum of the moments about where that R is applied. And the formula is P times RP minus RF, right? Because this is smaller. So that distance here is RP minus RF, right? It's giving you a counterclockwise moment, right? And TCD times RP plus RF is giving you a clockwise moment. Those have to balance to be in equilibrium. And again, we're sort of at impending motion. It's not moving, but we're just about to move. So everything is in equilibrium. And that's why we can do these moment equations have to be 0. And we can solve this then for P. So P is going to equal TCD, which is 108.7 times 25 plus 2. So that's your RF over 25 minus 2. And that gives you a P of 128 newtons. Ollie? RP, I circle it right here, it's 25 millimeters. That's the radius of the pulley. Yeah, it's called the radius of friction, and it's basically how far off the friction force is causing the contact point to slip. And that sort of is determining how much friction you're getting, right? Because the more it's slipping, the larger the friction force is, things will kind of have to shift more to accommodate that. So if the friction force is bigger, it's going to be more like that. And anyway, oops, this is something I don't know a whole lot about. I'm just pretending to. But you're going to get more of this. You mechanical engineers are going to see more of this, you know, in the dynamics class. So it's sort of a preview. But that was only case 1 where it was slipping. What about the case where it tips? So this is the sort of, you know, typical scenario. Does it slip or does it tip? Well, what if it's actually tipping? So let's go back and look at the free body diagram of B here and see what's the force that's going to make this thing tip, right? Suppose we have all these things going on here. Now the normal force is right at the edge, and B. Friction force is tugging along this boundary, FB. And TB is up like this. Well, all we got to do is figure out what is the force needed to, you know, get that thing. So we're going to basically find, you know, where does the sum of them, what at what tension or friction force do the moments equal 0 here, right? So point O, again, is this point on the left corner of the box where the normal force has shifted to? And the question is that going to stay on the box, or is it going to shift off? Or at what point are we at that corner? And then we kind of figure out that's smaller than the force it takes to slide the whole thing. So we'll do the sum of the moments at 0, at O equals 0. Sum of the moments at O, this point here, this the lower left corner. And that's going to equal TB times the height of the box, which is 400 millimeters, and minus WB times this distance here, which is half the width. That's 150 millimeters. And that will tell you, because of those ratios, that TB, we know what WB is. TB is going to equal 15 newtons, because WB is 40 newtons. And because the sum of the fx's equals 0, we know then that FB has to equal TB, so FB is going to equal 15 newtons. And in our previous analysis, it turned out that when we were causing it to slip between A and B, the friction force at B was 16 newtons. So we're not going to get that far. We're not going to get to 16 newtons. The thing's going to tip at 15 newtons. So it's actually going to tip. Darn. Well, we can propagate all that work we did to find the answer, and on A, we can take all those previous equations and find that it's going to take 57 newtons only to get that thing instead of 58 newtons that we found to make it slip. It's only going to take 57 newtons to get that thing to actually tip if you apply those other equations. We don't want to do that because it's late. And then we can go look at C and find that, well, that means that TCD then must equal 106.8 newtons. And then we can look at D and find that the P for that is just 125 newtons. So case 2 has a smaller P. So therefore, it happens first. So therefore, B tips. And our final answer is 125 newtons. It's kind of a capstone problem. It just involves a lot of these things in friction. Isaac? Yeah. If case 2 was bigger, a bigger P, then we would go with the first analysis. Yeah, the bigger P. So I mean, the assumption is that the assumption is that we're slowly increasing P from 0, right? And as we do, we're going to cross a couple points here. And one of the points is when P gets to 125 newtons, the box is going to tip over. And that reduces the friction on the box A, so it actually slips sooner than B is tethered to the wall. Yeah, but once B starts to tip, then the friction at B is kind of gone because there's just a little edge there. So the box at A slips out before that. Yeah, it's a complicated thing, and I'm also reminded, did you ever see those magic tricks where like the magician has a fancy table set up with all the cups and stuff on it with a tablecloth? And you know, if the magician pulls slowly, all of those things are going to fall off the edge, right? But if they do it really fast, it slips out. And I think that's sort of similar to this, right? In a way, right? If you do it really fast, if you could yank on the rope really fast, then the box probably would slip out without be tipping. But if you're going slowly, right, it's going to tip before it slips. Yeah. Yeah, if you can instantly accelerate the rope to 128 newtons and not stop at 125 newtons, which is kind of hard to do because they're so close together. But maybe if you took P straight up to like 200 newtons, and, you know, then you could probably scoop A out without the whole thing tipping over. But that's sort of I think that's the analog, the way how friction works. But we're sort of assuming that we're going to be slowly increasing P until something happens, and we want to know what is that minimum force for something to happen. And it's going to be the smallest one according to our assumptions. Well, the force is increasing slowly until something happens. Yeah, because this is statics. There's no speed, just force. Yeah, it becomes dynamics when that happens. Yeah, so that is it. Wow. And it's kind of late, come to the end of the session. So basically, tomorrow and Thursday we'll be doing in-class problems. And I highly recommend everybody show up for those because those are really where you learn this stuff, as you know. So I hope you're all here. We're going to really tackle these things, get as much done as you can before the weekend. This is complicated stuff, and if you don't actually work through it, you're not going to figure it out on the test. That's the thing.